So the first thing we're going to do is divide n intervals. So now we have to find the width of each interval. So we're going to go let delta x equal to the width of each subinterval. And remember, we made all the subinterval the same. So we'll call it delta x. So let me ask you this question, just in this. So if I have 0 and 2, let's say my interval is, let's change it. Let's say it's from 1 to 5, okay? And I tell you that I want to split this into two subintervals. So what will be the width of each one if the two widths have to be the same? You guys follow my question? I want to divide this interval 1 to 5 into two subintervals, and each of which is going to be of the same size. So what will be the width of each one? 2, because you'll split it up at 3. So this will be 2 and this would be 2. All right. So if you have two subintervals, you guys don't need to write this, but I'm just showing you will have each width will be 2. What if I want 4 subintervals? What will be the width of each one? Because you'll split that up into now 4. So the width will be what for each one? 1. Is that okay? If I want 8 subintervals, what will be the width? So you'll split this up into each one into half, right? So each one will be what now? 0.5. So can you come up with a formula from this? In general, what do you think the width formula would be? I want to find, so I did 8, but if I do 16 or 35 or whatever, I want to come up with a formula so I don't have to do this every single time. Do you guys follow? It doesn't matter what these guys are. If you use that formula, it'll always work out. So what do you think the formula is? Like, for example, if I want 8, okay? Could I do this? I could take 5 minus 1 over 8, which will give me what? 4 over 8, which will give me. You guys see that? Okay. If I wanted 4, I could have done what? 5 minus 1 over 4, which would give me 4 over 4, which would be. Do you guys see that? So what are we doing? We're taking this point, subtracting this one, and dividing by how many ever we want. If you want 8, I divide by 8. If I wanted 3, I could have also divided by 3. Doesn't matter. Is that okay? So the trick out here is to come up with a formula for delta x. All you have to do is find the length of the interval and divide it by the number of intervals you want. Is that okay? So in this case, we're going to take delta x is going to be b minus a, because b is the endpoint, over n. N is your subintervals, right? And n can be anything. In my case, like I said, I used n to be what? 1, 2, 3, 4, 5, 6, 7, 8 in my case, okay? You could make n whatever you want. It doesn't matter. So, okay? So this first one, I'm going to call x naught, that point, okay? Then the next one would be x1, x2, x3, x4, dot, 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 and this last one would be xn. Okay? In my case, n would be 8, so I would have x8. In your case, you might have done 7. You would have x sub 7. Is that okay? But we'll leave it like that. So it'll be just in general, and could be anything. You guys all follow? Okay. So that we have that. We already laid the game plan last time. I'm just writing it down now. Is that okay? So last time I told you we take one rectangle, then split that up into 2, then into more, into more, into more, into more, and eventually we got the right area, correct? So that's what I'm actually going to do it now by writing it out. So the next thing we're going to do is, okay, we're going to find the evaluation point I'll put in parentheses point to find the height of the rectangle. Because we're going to draw a rectangle in each interval, so I need to know where to draw the rectangle. So we're going to find the evaluation point. That is the point to find the height of the rectangle, evaluation point in each subinterval. Okay, that's what we're going to do. So let's go back up to the picture and do that. So so let's just focus on, if you just pay attention again, don't do this. So let's say this subinterval, that's my first subinterval, correct? I need to find an evaluation point. Why do I need to do that? Because that's going to be the point that I'm going to use to find the height of the rectangle. Because if I take, like, for example, let's say that this point hypothetically was 2. If I wanted to find the height of the rectangle at 2, then what would I do? I would replace this x with 2 and I'll find what? I'll find the height of the rectangle. You guys understand that? So I need to come up with a way to find that. Now I can, for example, I can use this as my evaluation point, the left one. I could use this as my evaluation point, the right one, or I could use the midpoint. Do you follow? Or I could literally use any point in between. And that's something we'll learn in the last section. Everything we are doing here, we're going to put some restrictions on everything we are doing today. But in the next section, you'll learn, even if I don't have those restrictions, it still all works. Do you guys follow? So, but for now, because of simplicity, I'm always going to use the right point to draw the rectangle. Okay. So I'm going to imagine this is my evaluation point. So I'll call them x hat sub 1, because hat means it's my special point where I'm going to find the height. Okay. So if I go up to the curve, that's going to where I'm going to draw the rectangle. That's going to be the height of my rectangle. Then I'm going to go across, and that's going to be my rectangle. Okay. So in this next interval, where's going to be my evaluation point? Always the right. And like I said, doesn't have to be, but for just simplicity, we'll always use the right one. Is that okay? So I can go up to the curve using the right point, go across, and draw my rectangle. Everybody get the idea? Okay. So this point will become what now? X hat sub, because that's my second evaluation. Do you guys understand that? Okay. So what do you think is the formula for x hat sub k in general? What do you think will be the formula to find the kth evaluation point? You guys understand my question? So let's pretend, if you, again, focus on this. Let's say that this rectangle that I've drawn is my kth rectangle. This is my kth rectangle. Do you guys follow? K could be some number. For example, if k is 2, then it would be this rectangle. You guys follow? If k was 2, it would be the second rectangle. K is just some number between 0 and n, because you have n rectangles, correct? So it's just some number between 0 and n. If k is 1, it would be the first rectangle. That's all it is. So if this is my kth rectangle, what will be the formula for this point? Because won't this become my evaluation point for that rectangle? And what did we call that? X hat sub k for the kth one. So what will be the formula for that? How far is it from the start? Start would be here, correct? That's my start. Okay. What is the width of each rectangle? I told you, what is the width of each rectangle? Delta x, right? Isn't that the width of each rectangle? So this is delta x. This is delta x. This is delta x. This is delta x, and so on, right? So how far is this point from A? Well, we can't use 6 because we don't know what k is. If k was 6, yes, then it would be 6 delta x. But do I know what k is? K is just some number between 0 and n. So it can be anything. It could be 1, 2, whatever you want. So it'll be how far from delta? It'll be k delta x's from the start, correct? Do you follow? If k was, like, for example, if k was 2, that would mean this point, correct? That means how far is it? 2 delta x's from the start. Do you guys understand that? So the formula for x sub hat to find that evaluation point is just going to be a plus k delta x. Why a? Because that's where it starts, at a. And then you're adding so many delta x's from the start to find that evaluation point. So now we have a nice formula to find where we want to find the height. So go ahead and draw some of those rectangles using the right-hand point like I've done. If you've already done it, great. But so at least draw a couple of them so you guys can get the idea. This goes up, goes across. So we're always using the right point, correct? And you continue this. I'm going to do a couple of them and I'll put dots the rest of the way. Okay, we're going to do the same thing across the board. Is that okay? So far we found delta x and we found how to find the evaluation point. Let's do step 3. Step 3 is we want to find the area of each of those rectangles, correct? Because if I add them up, that'll give me, by the way, if I take all of these rectangles and add them up, will that give me the exact area? Would that give me the exact area? No, I'm overshooting quite a bit here, correct? This is all overshoots, right? So my area that I get will be actually more or less more than what I, that's okay. But we can fix that. We talked about it yesterday, how to fix that, right? How do we fix that? Take more and more rectangles. The more rectangles you take, the smaller the overshoots will get. Do you guys understand that? Okay. All right. So I want to find the area of all of them. If I take all of these areas of all of these rectangles and add them up, that'll give me a good approximation. It won't be the correct approximation, but it'll still be a good approximation. So let's do that. So let's do the next thing. We're going to add up the areas of n rectangles, because remember we have n rectangles, correct? You guys agree? So you guys help me, okay? So area of n rectangles, I'll put n here. It'll be the area of what? The first rectangle plus the area of the second rectangle plus the area of the, and all the way up to area of n rectangles, because we have n rectangles, right? All right, let's do it. You guys help me. What is the area of the first rectangle? Think about it for a second. Area, what is the area of a rectangle in general in geometry? Length times width. Okay, so what is the length of the first rectangle? The length would be this guy, correct? The height of the rectangle. The width would be this, correct? What is the width always? We already said it's always going to be delta x. And the height would be the height at the evaluation point, right? X adds up 1. Is that okay? Of the function. So the area of the first one would be delta x. I'm sorry, that's wrong. Length, which is f of x hat sub 1 times delta. Why f of x hat sub 1? Because we find the height of the function at that evaluation point, correct? That'll give you the y value of the function. Do you guys follow? What is the area of the next one then? F of x hat sub times delta x plus all the way up to n, which would be f of x hat sub n of delta x. Correct? Is that going to give me the right area? No, it's give me a good approximation. So this is an approximation, correct? This is an approximate area, but is it the right area? No. One of the things we learned in the last yesterday, that I can write anytime you have a sum, we can write it more compact using the summation notation. So that's what we're going to do here. So I'm going to write this in a more compact form using a summation notation. So summation out here, k starts at 1 and goes up to n, because it starts at 1. You can see that it starts at 1 and goes up to n, correct? And then what are we adding? We are adding f of x hat sub k times delta x. When k is 1, you can see that clearly. When k is 1, it gives us this term, doesn't it? And then when k increases, you put a plus sign. Now k becomes 2. That gives us this term, right? Then you increase k, so you put a plus sign, then k becomes 3. That'll give us the next one, next one, next one, till we get all the way up to. It's just a compact way of writing it. Is that okay? So this is the area of n rectangle. So this is an approximation, approximate area. And from the picture, we were clearly able to say that it was overshooting, correct? Sometimes it'll undershoot depending upon the function. Is that okay? We don't know that, but at least we know it's not the exact area. Is that okay? All right. Now that we have that, the step 4 is to find the actual area. Step 4 is to find the actual area. We want to find the exact area, not an approximation. And what did we establish yesterday we were going to do to find the exact area? We're going to imagine how many rectangles we have. Infinite, okay? So to find the actual area, which I'll call A, is going to be the limit as n goes to infinite. The only way we can understand, use the concept of infinite if we take limits, because that lets us imagine we have infinite rectangles, because there's no way to imagine infinite rectangles because we don't know what infinite is. Is that okay? So the next best thing we can do is we can approach infinite. We can see what happens when we get close to infinite. Is that okay? Of a sub n. Why a sub n? A sub n is the number of n rectangles, right? Like for example, I'll come back to that. Let's say hypothetically n was 100. So n would be what? 100. You guys follow? But if I want to imagine I have more rectangles, what will I do? I would make n to be, let's say, 1,000. So we're just increasing n. So when we take infinite, we want this to be what now? So we want to take infinite rectangles, right? So you want to find a sub n of infinite. Is that okay? So that's why we are writing it this way. Is that okay? We are imagining we have infinite rectangles. I have a formula for this. I'm going to replace this with that formula, which is, what was it? It was summation k is equal to 1 to n f of x hat sub k delta x. And this formula will give us the exact area. You guys follow? It'll give us the exact area, which is really cool. We can do this and find, doesn't matter what weird shape we have, we can find the exact area. So this is the first way the Greeks decide, not Greeks, sorry. Euler and Newton, not Euler, Leibniz and Newton did this. Do you guys follow? They figured out how to do this. All right, so let's take a look at an example. Everybody okay with us? Now to do this, I gave you some really important formulas. We're going to need all of these formulas that I gave you last time. Because remember, I gave you these properties of summation, So these are all these formulas. Without this, we cannot do any of this that we're going to do next. Is that okay? So it's important that we know those formulas. All right. I'm going to start with a problem whose area we know how to find just to see if this works. You guys follow? We're going to start with a problem of a function whose area we know how to find. So let's say if I give you this function, f of x is equal to 2x plus 4 on the interval. Okay, let's go from 1 to 5. Let's just do that. Okay, now before I do it, find the exact area using the method we came up with. This method will be an overkill for a problem like this, because this problem I can find the area geometrically. Is that okay? But let's do it so we can verify the method to see if it actually is working. So let's graph this function and first find the area, then we'll use the method to find the area and see if the two answers are the same. Okay? So I'm going to graph this line. So I'm going to scale this by 2. So we have 2, 4, 6, and I'll scale this by 2s also. No, I'll scale that by 1 since we're starting at 1. 1, 2, 3, 1, 2, 3, 4, 5. Again, I'm just doing this to show you that this method works for something like this, okay? So let's draw the function. This is a line, right? This is an equation of a line. So the y-intercept is 4 and the x-intercept is -2. Oops, why don't I put negative signs on these guys? Okay, that is my line. So I'm going to draw that line. So it looks something like this. Good. So that is a function. That is a function that was given to us. Y is equal to 2x plus 4. I want to find the area under that curve between what? 1 and 5. So here is 1. And here is 5. So I want to find this area. Is that okay? Yesterday, we did this problem by doing what? Splitting it up into a rectangle and a triangle and doing that. So let's just do that and then we'll do it. So I'm going to do this at the bottom here. And again, I purposely picked this problem just to show you that the method works, okay? On something whose area we know how to find. So I'm going to split this area into 2 pieces, area of a rectangle and area of a triangle. So let's split it up. So this is going to be split here. So this is my area of a triangle, and this is the area of a rectangle, right? So what is the area of the rectangle in this problem? What is the length of that rectangle? That would be this guy. What would that be? That'll be the value of the function here, right? Whatever this point is, isn't this the same? So you plug in 1 into the function, you'll get the height, right? What is, it's not clearly drawn to scale, you can see that. Because when I plug in 1, you get what? 2 times 1 is 2 plus 4 is 6. So this point really should be 6. Is that okay? So let's say that 6 is my height. What is my width? What is the width of the rectangle? No. The width would be this, correct? So it's 5 minus 1, which would be 4. Is that okay? All right. Plus 1/2 base. What is the base of the triangle? 4. And what is the height of the triangle? The height of the triangle would be this distance, correct? On the top. So I need to find this point and then subtract 6 from it because we know this is 6, right? So I need to, so I plug in 5 in here. That'll give me the height at that point, you know? So you'll get 10 plus 4 is 14. 14 minus 6 is what? 8. So this would be 8. You guys understand that? So we'll end up with what? 24 plus 16. So we'll end up with 40. Now, this method that we came up with to find the areas, it's for shapes that are not geometric, for which we don't have formula. But this one is clearly geometric, right? We do have perfectly good formulas for this. But remember, this method works for non-geometric shapes. Are we clear? But for now, let's do it using this method and see if it actually works. Okay. So the first step is what? If you recall, we want to split it up into n subintervals, right? This interval. I'm taking each of these steps. I'm going to go through 1, 2, 3, and 4. Is that okay? So we split up into n subintervals and we found delta x. What was the formula for delta x? It was b minus a over n. So what does that become? So we get delta x. What is b in our case? 5, and a is 1. So you get 5 minus 1 over n, which will give you what? 4 over n. So do we know what delta x is? It's going to be 4 over n. Are we good? Next thing we're going to do is we're going to find the area. What was the next thing? We're going to find the right endpoint, correct? The formula is right here. It's the evaluation point, you know, which was what? X hat sub k is equal to a plus k. So we get what? X hat sub k is equal to a plus k delta x, right? That is a formula we came up with to find those evaluation points, you know? The hats are the evaluation points. So what does that give us for x hat sub k? What is a? 1 plus k, and what is delta x? 4 over n. So we have a formula for x hat sub k. It's 1 plus 4k over n. All right. Step 3. I wanted to find the area of n rectangles, correct? So how did we write that? We wrote a sub n is equal to the summation. We added up all those rectangles, correct? And to do the adding, we use summation because we're going to do the same thing to each one. K is equal to 1 to n. And we had what? F of x hat sub k times what? Delta. The height of the rectangle, the length of the rectangle times the width. You guys remember that? This is the length and this is the width. And we started adding, multiplying and adding them up, right? For each of those rectangles. So let's plug this in. What do we know here? We get summation k is equal to 1 to n. What is f? F is my function here, correct? You guys follow? So just keep that in mind. I'll come back to that. What is x hat sub k? X hat sub k is, so it's this, is 1 plus 4k over n, and delta x is what? 4 over. All I did, I just plugged in things we already know, right? Now what do we do next? I know my function. So if I told you find f of 5 like we did a minute ago, what did we do? We replaced x with what? 5 and we ended up with 14, you know? You guys remember that? Instead of plugging in 5, we're going to plug in what? 1 plus 4k over n, because that's what we want to do. We want to find the height at this point, right? So let's do that. So we get summation k is equal to 1 to n. We get, what was my function? I'll write it down here. It was f of x was what? 2x plus. So I'm going to replace this x with what? All of that. Is that okay? So we'll get 2 times 1 plus 4k over n plus 4. Are we good so far? I'm going to distribute and then I'm going to collect some terms and then see what we get. So can you guys help me so I can save a step? What happens if I distribute? I'll get what? 2 plus 8k over n plus 4, correct? I have that 4. I can collect what? 2 and the 4. So we get 6 plus 8k over n times 4 over. Good so far? Next, we're going to go ahead and distribute that 4 over n, and that'll be our final answer for this part. So we get k is equal to 1 to n. We get 24 over n plus 32k over n squared. So that is my formula for the sum of n rectangles. Do you guys see that? If you tell me n is 2, I can replace n with 2, and that'll give me the answer for 2 rectangles and 3 rectangles, whatever you want n to be. Is that okay? Good so far? So we did with step now. We did step 3. That gave us a good approximation, right? Are we interested in the approximation? No, we want to find the actual area. So all we're going to do next is what? Take the limit. So let's do that. So step 4, to find the actual area, we're going to take the limit as n goes to infinite of this guy, because we're going to imagine we have n of them, right? So let's replace that limit as n goes to infinite of the summation k is equal to 1 to n, 24 over n plus 32k over n squared. What I'm going to do next, I could have done up here, and maybe in the next problem I'll do up here, so we don't have to keep writing the word limit all the time. Is that okay? So maybe next problem I'll do that, but let's finish this. Are we good so far? Okay. So we're going to use properties of summation now to rewrite this, okay? One of the properties of summation is you can distribute a summation, and anything that doesn't have anything to do with k can be taken out. That's one of the properties of summation. Okay? So anything that does, so like for example, is there any k in here? No, so I can take it out, and then I get summation k is equal to 1 to n of just 1, because I took everything out. Is that okay? From the second term, what am I going to take out? I can take out a 32 over n squared. So I'll take out that, and I'll be left with what now? Just k, right? Because that's left. Good? 2 more lines and we are done. If you go back and look at your notes, what is the summation of 1? This is where you need those formulas. Without that, you cannot do that. Summation of 1 is what? Whatever this variable is, n. Is that okay? And then we're going to need summation of k. Summation of k is what? That. Is that okay? So we're going to need both of these formulas. They were in the video that I sent out yesterday. Okay. So in this case, we're going to end up with 24n times n, because summation of 1 is n, plus 32 over n times summation of k, which is n times n plus 1 over 2. That was a formula for summation of. Good. Now let's clean this up. One of the properties of limits is what? You can distribute a limit, right? So I'm going to do that. And as I distribute, I'm going to clean it up. Like, for example, in this case, the ends will cancel. In the first case, I'll just get limit as n goes to infinite of just 24 plus the limit as n goes to infinite. What cancels here? One of the n's cancel and one of the 2's cancel. So we get 16. Forgot something. Hold on. Oh, what did I forget? N squared, right? So one of the n, because there was an n squared here, right? So I forgot to write the square. So one of the n's will cancel, okay? Not all of them, because that wouldn't work. Is that okay? And then you'll be left with what? N plus 1 over n. Is that okay? Because one of the n's will cancel. Are we good so far? Way back in chapter 2, we learned limits. And we are taking limits where? At infinite. If you remember when you just did that in the last chapter to chapter 4 when we did asymptotes. When we take limits at infinite, we just keep the dominating terms on the top and the bottom. So let's do that. A, in the first case, there's no n. Do I even need limits there? No, the answer is just 24 for that, correct? In the second case, I'm going to keep the dominating terms on the top and the bottom. What's a dominating term on the top? 16n when you distribute, okay? And what's a dominating term on the bottom? They will. Again, do we have any n's left now? So you end up with what? 24 plus 16, which is what? Does this method work? Yes. Overkill, right? But why is it an overkill in this case? Because we have a geometric formula for that. But what if I give you a weird function? Well, do we have a geometric formula for some weird shapes? No. So that's where this method pays dividend. Do you guys follow? This method is really good when we start doing weird functions. So let's take a look at the next example, which is a weird function. So let's say if I give you f of x is equal to, let's do x squared plus, oh, let's do you want to do plus or minus? Pick a sign, guys. Minus 4, okay, on the interval 1 to, let's do 2 to 4. Okay. Let me graph this to show you what's going to happen. Is that okay? So let's graph this. So this function looks like this. This is 4, this is 2, this is minus 2, this is minus 4. I want to find this area between 2 and. Is this a shape whose area we have in geometry? Yep. So can I use any of geometry to help me with this one? Yeah. So this is where this method will help us. Do you guys follow? This is a fantastic method. It'll give us the exact area. You guys imagine, like I told you yesterday, imagine you're an engineer and you're designing a part like that, shape like that, and you want to find how much material you're going to need. So this is a perfect example for that. Okay, are we good? So I've convinced you the method works, right? I convinced you with the last example the method works, and now I'm showing you that here's an example that we don't have any way to find the area in geometry. Is that okay? So we're going to use this technique to find the exact area. So let's start. What's the first step? You divide the interval into n subintervals of equal width, right? And we call that what? Delta x. So we need to find that, which was what? B minus a over n. So in our case, what is b and what is a? It's 4 minus 2 over n. So it's what? 2. Do we know the width of each interval? Yes, it is 2 over n. For example, if n is 2, the width of each interval is 1. You guys follow? If n is 10, the width of each interval is 1/5. You guys understand that? It just gives us a blueprint on what the width is. The second step was what? To find the evaluation point, x hat sub k, because we want to find the height in each of those intervals, correct? I want to find the height of the rectangle or the length of the rectangle, which was what? A plus k delta x. By the way, these problems get very, very easy is if a is 0. Out here, a is what? 2. Still makes you do more work. If a is 0, it'll become very, very fast. Do you guys follow? If a is 0, this problem will become very fast. But for now, we'll just do it. So this gives us x hat sub k is equal to, a lot of your problems for homework are a is 0. Is that all right? So it'll go quicker. So we'll get 2 plus k times 2 over n, right? Because delta x is 2 over n, a is 2, right? Are we good? Next step is what? Find the area of n rectangles. And to do that, we added them all up using the summation notation by taking the height of each rectangle and multiplying it by the width of each rectangle, right? Using k's that gave us each one. When k was 1, that gave us the first rectangle. When k was 2, it gave us a second rectangle, and so on. This time, I'll come back to this if you didn't copy. I did a lot of work with this limit stuff here, and then we had to keep writing the word limit. So what I'll do this time is I'll simplify all the way up to this point, and then we'll just take the limit and we'll be done. Is that okay? So it'll be the same idea, but just so we don't have to keep writing limits all the time. All right? Now what do? We plug in our x hat sub k here, which was what? F of 2 plus 2k over n times 2 over n. Delta x was 2 over n, right? Correct? I'm just plugging in what I know. What does this mean? This means find the value of the function f at this point, correct? So what was f? F was x squared minus 4. So what am I going to do? I get f of what? 2 plus 2k over n. What does that mean? You would take 2 plus 2k over n, and you're going to do what to it? Square it minus a. Everybody agree with that? So let's clean that up a little bit. You know how to expand, right? I'm not going to do that. You take this times this, multiply by itself, So we're going to end up with 4 plus 8k over n plus 4k squared over n squared minus 4. Everybody okay? The nice thing is what in this example, the 4s will cancel. So I'll come back and plug it in here. So I get summation k is equal to 1 to n. I have 8k over n plus 4k squared over n squared times 2 over n. If you don't follow something, please make sure you guys ask me. When you really think about it, when you take a step back and think about it, there's nothing difficult. We're just doing algebra here. You guys follow? All we're doing is algebra. What is the next thing we do? We distribute this guy. Okay, so let's do that. We get k is equal to 1 to n. We get 16k over n squared plus 8k squared over n cubed. Now, in the last problem at this stage, I went to the next step. But in this problem, I'm just going to simplify this while I have it in front of me. Is that okay? Just so I don't have to keep writing the word limit in the front, So I'm just going to simplify this. One of the things we can do right away is what? Distribute the summation and take out anything that doesn't have anything to do with k. So I get 16 over n squared. This summation of k is equal to 1 to n of k plus 8 over n cubed is summation of k is equal to 1 to n of k squared. Are we good? Do we have formulas for summation of k? I gave you that yesterday. We also have a formula for k squared. I gave you that yesterday. Okay, so I'm going to put those in, and then we'll go to the next step in here. So the summation of k is n times n plus 1 over 2. And like I told you yesterday, and I'm telling you that today. Without knowing those formulas, there's no way to do these problems. But okay, you need to know those formulas. Plus 8 over n cubed times n plus 1 times 2n plus 1 over 6. That's a formula for summation of a squared. So that's where I'm going to stop for this one now. So this is the sum area of n rectangles. This gives us a good approximation. If n is 2, you replace all the n's with 2, and that'll give us a good approximation. If n is 3, I'll replace all the n's with 3, and so on. That'll give us a good approximation. It'll give us the exact answer? No. So now to get the exact answer, what are we going to do in step 4? We're going to imagine we have how many rectangles? Infinite. So we go a is equal to the limit as n goes to infinite of a sub n. A sub n is all of that, correct? So let's do that. So I get limit as n goes to infinite. Let's clean this up along the way. One of the n's will cancel. The 2 will become a 8. So I'll get 8 n plus 1 over n. Right? What about the next one? One of the n's will cancel, right? And this 6 will become a 3, and this 8 will become a 4. So we get 4 times n plus 1 times 2n plus 1 over 3n squared. You guys agree? We just cleaned that up. And now we take the limit. One of the nice things about limits is what? We can distribute the limit, right? We can do term by term. But the other nice thing is what? We are taking limits where at? When we do infinite, we just have to worry about the dominating term. So I don't need to write anything extra. So let me do that. So I'll distribute what's a dominating term for the first one. 8n over n plus the limit. What's a dominating term in the bottom of the second one? 3n squared. And what's a dominating term on the top? Yes, because you would multiply this and this, I'll give you 2n squared, and then you'll multiply that by 4. So it's actually 8n squared. That'd be good. These x's will. Do I have any more n's left? No, so I don't need to take limits. So I'll just get a 8 plus these n squares will cancel. Do I have any more n's left? No, so it'll give us what? And then we do the common denominator and add them up. So you get 24 plus 8 is 32 over. And this is the exact area under that. Not an approximation. This is the exact area. Isn't that cool? We were able to do that. In the last problem, we had this geometric shape, right? That we were able to verify. But now, do we have a geometric shape? No. The nice thing is if you have a TI calculator, you can easily check this. If you have a TI calculator, you can push it in and you can check it. So I can go to math 9. I can type in my function. What was my function? X squared, was it? Minus 4. You wanted times x. We went from 2 to 4, correct? When we get 10 point that, which we had what? 32 divided by. Okay, so that's the exact area that we just found. Pretty good. I know some of you have class, but I would like to do one more problem before I let you go, but I will give you the homework. If you have class, you guys can more than welcome to go. But I want to definitely do another problem so you guys can see. Let me give you a homework. So this is section 5. 3. Is that okay? Area under the curve. And again, if you haven't watched the videos, the formulas that I'm using up on the video, is that okay? So make sure you guys do that. So we did a problem just like problem 1E, except we had x squared plus 4. Out there is x squared plus 1. Is that a different problem? No, it's pretty much the same, okay? So I want you to do problems. I'll give you 3 problems. Someone pick between 1 through D, letter 1 through D. Actually, let's want A and B because that starts at 0. I told you zeros are really nice. So let's do either A or B. Pick one. Okay, so you can do 1A. Then you can do 1E and then 1H. So I've given you a little bit of everything. I'm going to do one more really quick, and I'll do 1F, x squared plus 2 from 1 to 3, okay? So this problem is f of x is x squared plus, let me do a different one. You don't have to worry about, let me do what you guys have so you guys can have something to look back on. Is that okay? So I'll just do x squared plus 2 on the interval. Let's go from 1 to 5. Is that okay? All right, so let me graph this to show you what this looks like. This is 2. The function goes like this. This is 1, and let's say this is 5. This is the area we are looking for. Is this a geometric shape? No. Do we have any formulas in geometry to find that? No. But let's see if we can use our technique to find the exact area. Are we good? Okay. All right, first step. What did we find? You guys tell me now. Sorry? What do we find? Delta x. So what's the formula for delta x? It's b minus a over n. So what is delta x in our case? It'll be 5 minus 1 over. Actually, let's do this. I'm tired of even numbers. Let's make this a 6. Is that okay? Let's change that to a. So what will we get this time? 5 over n. Everybody okay with that? 6 minus 1 over. And again, like I told you, if it was 0, it's much nicer. It's a lot cleaner. You'll see that when you do that first problem for homework, okay? Second thing is what? What do we find? The evaluation point where we want to find the height, right? Which was what? A plus k delta x. So what will that give me? Come on, tell me. What is x hat sub k? Will be 1 plus 5k over n. Did everybody get that? Did you guys get that? Because a is 1, delta x is 5 over n, right? What's the next thing we do? Find the area of n rectangles using this formula. F of x hat sub k. And you don't have to memorize this formula. You can see this is the length, this is the width. Do you guys follow? There's nothing to memorize here. This is length times width. Okay. So let's plug it in. So we get summation k is equal to 1 to n f of x squared plus 2. Oh, sorry. What is x hat sub k? 1 plus 5k over n times delta x, which is 5 over n. Good. Now we're going to do some scratch work on the side. So I want to find f of 1 plus 5k over n. What does that mean? In the function f, I'm going to replace every x with what? 1 plus 5k over n. So I get 1 plus 5k over n squared plus 2, was it? Okay. Very good. Then what do we want to do? We want to expand it, right? So I'm going to expand it for you just for the sake of time. I'll get 1 plus 10k over n plus 25k squared over n squared plus 2. You guys know how to expand, right? You just take 1 plus 5k over n times 1 plus 5k over n. What can we do to these guys? We can collect them. So I'm just going to write that here so I don't have to rewrite that whole thing. So when I plug it in here, I'll add them up along the way. So I'll get 3 plus 10k over n plus 25k squared over n squared 5 over n. So all I did is add that 1 and the 2. and we plug that in. Are we good? Then we're going to go ahead and distribute the 5 over n. So let's do that. So we get 1. So we get 15 over n plus 50k over n squared plus 125k squared over n cubed. 2 more steps. Good so far? Then what do? We go ahead and distribute the summation. Anything that doesn't have a k in it, we can pull out. So let's do that. So we get, in the first term, everything comes out. So if everything comes out, we always left with what? 1. If everything comes out, you're left with 1. Plus we get 50 over n squared summation of k plus 125 over n cubed summation of k squared. Good. Now we just have to use those formulas I gave you yesterday to plug them in. Again, you can, I'm hoping I've convinced you without those formulas, none of this will matter. Is that okay? So this is a sub n. I get 15n times n, because summation of 1 is n, plus 50n squared times k, which is n times n plus 1 over 2, plus 125 n cubed times n plus 1 times 2n plus 1 over 6. These are just formulas that I gave you last time. Is that okay? So that is the area of n. So for example, if you want to find, if you had 5 rectangles, you would replace n with 5, and that'll give you a good approximation. It won't give you the exact area, but it'll give you a, if n is 100, you would replace n with 100. Is that okay? So that's all we are doing. All right, the last step is to find the actual area. We're going to take the limit as n goes to infinite of a sub. Okay, so let's do that. Limit as n goes to infinite of a sub n. A sub n is right here. This is what a sub n is, right? We just calculated that. So I'm going to clean it up as I write it down. So I get 15 because the n's will, one of the n's will cancel here. The 2 will make this a 25. So we get plus 25 n plus 1 over n, plus one of the n's will cancel here. Okay, and the 6, oh, 6 doesn't cancel this time, does it? Right? So we'll get what? 125 n plus 1 times 2n plus 1 over 6n squared. So all I did is simplify it along the way. And one more line and we are done. Next thing we do is what? Distribute the limit. And as we distribute, we're going to keep the dominating terms because that's all that matters. Now, before I do that, in the first case, when I distribute here, are there any n's here? No. So do I even need the limit there? No. So I'll just get 15 for that one. Plus, I get limit as n goes to infinite. The dominating term is what in the second one? 25n over n. And in the last one, what is the dominating term? We have 6n squared on the bottom, correct? What's the dominating term on the top? Remember, to find the dominating term, the good way to do that is take the dominating term in each parenthesis. This is the dominating term in that parenthesis, correct? And what is the dominating term in this one? And then on the outside we have, because technically that's another parenthesis, right? So you multiply all the dominating terms to get the dominating term. You guys follow? You take each one and then you multiply them. So you'll get what? 250 n squared. Are we good? Nice thing is these will cancel, so will those. Are there any ends left anymore? Do I even need limits for any of them? No, so we just need to add what? 15 plus 25 plus 125 over 3. Because I reduced the 250 and the 6, you know. Okay. So just add them on your calculator. What do we get? Common denominator is 3. 25 plus 15 is 40. So 40 times 3 is 120. 120 plus 125 is what? 245 over 3. Right? Let's just quickly check it. Just make sure we did it correctly. First of all, I'll type in 245 divided by 3. This is what we want, right? 81.666 something. So let's see if we get that. So our function was x squared plus 2, right? Oops. And then we went from 1 to 6, right? Okay, so we got the right answer. Now, before I let you guys go, I gave you the homework, right? Before I let you go, long ago in chapter 3, if you recall, when we first learned derivatives, we used this method to find derivatives. The difference quotient. Do you guys remember that? We used this, and that was really long, right? And then in that same chapter, we learned what? We learned shortcuts, right? Correct? Those are all those formulas like derivative of x squared is 2x, derivative of x cubed is 3x squared. We learn all those. Did we have to use this formula anymore? No. But that formula was tedious. If I wanted to find the derivative of, let's say, my function was x cubed, that formula took us a while to do that, right? You had to expand it, then you had to collect the terms, and you had to take the limits and stuff. But then using shortcuts, we could do it in one line. So now in chapter 5, we are doing the same thing. We learned how to find the area using what we just did today. Okay, so this is the area method is basically we have what? A is what? The limit as n goes to infinite, we have summation f of x hat sub k times delta. That's a long method. Do you guys follow? It took us like, look at how long it took us to do this, but still pretty elegant. It's still, but it's took us a while. Okay. In 3 sections from now, we're going to learn a shortcut to do which will take us a line, just like before. Do you guys follow? So we'll be able to do the same exact thing using a shortcut. Okay, and the shortcut is this, just to show you, we had 1 to 6 that we just had, and we were integrating what? X squared plus 2 dx, right? You guys know how to integrate this, right? What's the integral of x squared? X cubed over 3. What's the integral of 2? 2x, right? And then you're going to evaluate that from 1 to 6. So you plug in your upper limit. So we get 1/3 plus 2. I'm sorry, that's wrong. You plug in x, replace x with 6. So you get 72 is what you'll end up with, plus 12 when you plug in 6 for x, you know? Is that okay? And then you're going to subtract, you plug in 1. So you get 1/3 plus 2. So if I do that, I'll get 72 is what? 84 minus 6 plus 1 is 7 over 3, right? 84 times 3, we need a common. 84 is 240. 240 plus 12 is what? 250. 2 minus 7 over 3, which is 245 over, which is what we had, right? Okay, so this is a shortcut of doing the same thing, which we'll learn in a couple sections. This is actually called the fundamental theorem of calculus. This is the big thing about calculus. Okay, it's called the fundamental theorem of calculus. All right, you guys have a very, very safe weekend. Drive carefully, and we will see you guys back on Monday. You guys have your homework, right?